We are on FRQ topic number 8, motion on a curve. So this is a continuation from rectilinear motion, but now we are traveling along a curve. So again, if you need some refresher on the equations, this was a very formula-heavy topic. So if you need a refresher on those, be sure to go back and look at the very first page of the notes for this unit. We are just going to dive in and start on some FRQs. So the last time that this was on the AP exam was in 2018, and it was a shared problem. There were some parametric parts and some polar parts back in 2018. And you see, it's a little bit hit or miss whether these types of problems are going to show up. If they do show up, normally they are with a calculator. We're going to start with the problem from 2016. This was number 2 with a calculator. So let's get started on it. It says, at time t, the position of a particle moving in the xy plane is given by these parametric equations, and they give us dx dt. And it says that the graph of y, consisting of 3 line segments, is shown at the figure on the right. So this is the graph of y, not y prime, y. And then they give us an initial condition. So at time 0, this is the position of the particle. So that is telling us that x at 0 is 5 and y at 0 is 1, which we could read right here from the graph. Y at 0 is 1. But we would not know this x coordinate if they didn't give it to us. Part A, find the position of the particle at time 3. Well, if they give you a position and a rate, you can get any new position using the fundamental theorem of calculus. So I'm going to set up two equations for the fundamental theorem of calculus, one for x, one for y. First of all, x at 3 minus x at 0 is going to be the integral from 0 to 3 of x prime of t dt, which is given to us. We can call that dx dt or x prime, right? So x of 3 will equal our value for x of 0 that they gave us, plus this integral, and now we're going to our calculator. I'm going to go to our home screen, clear out what's there, and I'm going to put our x prime in for y1, still in function mode. Double check, make sure you got it in there right. And then on our home screen, 5 plus the integral 0 to 3 of x prime dt. And so at time 3, the particle is at the x coordinate 14.377. For the y coordinate, y at time 3, if we want y at time 3, we don't have to set up first fundamental theorem because we have a graph of y. And y at 3 is right here, which is a negative 1/2. I know it's a negative 1/2 because they tell me these are line segments, and if they give us this grid, if they give you the grid, we can make the assumption that that is exactly at the point 2, negative 1. This is exactly at the point 4, 0. If they give you the grid, you can make those assumptions, okay? If they do not give you a grid, you cannot make that assumption. So it's nice that they did that this time. So y at 3 is a negative 1/2. If we did the first fundamental theorem, we would get the exact same thing, but we don't have to. So at time 3, the position of the particle is 14.377 negative 1/2, or negative 0.5. I usually use the same kind of notation that they gave me in the problem. So if they give me parentheses, I'll give them parentheses back. This part was worth 3 points. 1 point for the integral. 1 point for uses the initial condition. And 1 point for the answer. So, integral, initial condition, and the answer. Okay? Be sure to set this up. They need to see this. They need to see it. So, show them your work. Communicate what you're doing. It's part of the challenge. Part B, find the slope of the line tangent to the path of the particle at time 3. Remember that slope is always dy dx. That's dy dx. So we need dy dx at time 3. So dy dx at time 3 is, remember from parametrics, dy dt at time 3 divided by dx dt at time 3. That was what we did with parametrics. Dy dx is dy dt over dx dt. And dy dt at time 3 is the slope of y at time 3. And I'm saying it that way because we're given this graph of y. So what is the slope of y at time 3? Well, the slope is up 1 over 2, so it's positive 1/2. dx dt at time 3 I can get using my calculator, so I'm just going to write it like that. So I've got 1/2 divided by dx dt at time 3, and remember that dx dt is what is in our y1. So it's going to be my y1 evaluated at time 3. So we get 0.050, rounded to 3 decimal places. This part was just worth 1 point for the slope. Remember to never put a number down without saying where it came from. Part C, find the speed of the particle at time 3. Another formula for us. Speed is just the square root of x prime squared plus y prime squared. That's what speed is. So speed at time 3 will be, all right, well, x prime at time 3 we can find out. That's what we did right here, right? Y prime at time 3 is the 1/2, right? We found that out here as well. It's the 1/2. So this is going to be, and since we already found it out up here, I don't have to say what that is. Okay, so square root, parentheses, my y1 at time 3 squared, that will be that part, plus 0.5 squared, or 0.25. So this will give us 9.969. This was worth 2 points. 1 point was the expression for speed, and 1 point was for the answer. Part D, find the total distance traveled by the particle from 0 to 2. Another formula. This is the integral of the speed. The integral of the speed. So this will be, well, Actually, there is a little bit more to this, isn't there? Because we don't have an equation for y prime. This is not a problem, that's in our calculator, but this is a little bit of a problem. From 0 to 2, we need to find out what the slope is of y. So from 0 to 2, I see that we have two different slopes. So I'm going to need to split this integral up into two pieces. From 0 to 1, and from that, on that interval, the slope of y is a down 1 over 2, down 2 over 1, so negative 2 squared. And then from 1 to 2, the slope is 0, so that won't factor into anything. Now I can go to my calculator. So I'm going to have the integral 0 to 1 of the square root of my y1, not evaluated anywhere, squared, plus 4, plus the integral from 1 to 2 of, that's going to be the absolute value of x prime, but I'm just going to go ahead and type it in the way I think you guys would do it. This is y1 squared. And we get 4.350 if we round to 3 decimal places. This was worth 3 points. 1 point was for the expression for distance. One point was for the two integrals, breaking it up into two integrals. And 1 point was for the answer. So that was from 2016, and I think it was a very straightforward problem. This is one that you might be able to work quickly and accurately and get a lot of points from, and then spend a little bit more time on a different problem. Next up, I would like to take a look at our problem from 2012. 2012. Let's do 2012. Number 2 with a calculator. Alright, so it says for time greater than 0, greater than or equal to 0, a particle is moving on the curve so that at time t, we're at x of t, y of t. At time 2, the particle is at position 1, 5. So again, they're giving us x at time 2 is 1, y at time 2 is 5. Remember that when they give us this, we can, if we have information about the derivatives, we can find any other point. First fundamental theorem. They give us both x prime and y prime here. That's great. I love it when they do that. So let's go back to our calculator, and in for y1, I'm going to put x prime, and in for y2, I'm going to put y prime. So square root t minus 2, all divided by e to the t, goes in for y1, and sine of t squared, that's how we have to put in sine squared, right? Goes in for y2. Now, as we saw in that first problem, if I think about it, and if they give me both x prime and y prime, I like to go ahead and put in my speed square root, the square root for speed, which will be the square root of y1 squared plus y2 squared, since I have x prime in for y1 and y prime in for y2. Okay, now you may also want to put in the slope equation. The slope is y2 divided by y1. Now that's easy though to put into our home screen. Both of these are easy to put in our home screen. So this is totally optional. Putting in Y3 and Y4, totally optional. But I do like to do that if I think about it. And it doesn't take long. Okay, part A. Is the horizontal movement of the particle to the left or to the right at time 2? Horizontal movement. Horizontal movement, remember back from last unit, horizontal movement only deals with x prime, which they give us. So they're asking, is x prime positive or negative at time 2? Well, that's really easy to find out. dx dt at time 2 is equal to what? Well, that's just our calculator. So y1 at time 2 is equal to, oh, something's off here. Hang on. What did I do wrong? Oh, I put a plus in there. Oh, goodness. That would be bad. I'm sure you guys all noticed that. That would be bad. So I didn't double check. I usually double check, and this time I didn't double check to make sure my equations were the same. Fortunately, I got 0 here, and it told me that there was something else. I was really lucky that I made that error. Okay, let's go do that again. That looks a little bit better. So we get 0.271, which is positive. Therefore, the horizontal movement is to the right at time 2. Okay? And now we want to find the slope of the path of the particle at time 2. Well, the slope at time 2 is dy dx at time 2. AP needs to see what we're doing. We are putting in dy dt over dx dt at time 2. AP needs to see that, okay? Otherwise you may not get credit for your answer. So our slope was, I did put that in for y4. So I'm going to be pulling up y4 at time 2. And I get 3.055. In our first example that we did, I wasn't able to put all of these in, only because I didn't know what y prime was. I didn't have any function for y prime. But if they give me x prime and y prime, I do tend to do that. Okay, this part was worth 3 points. There was a little bit involved there. 1 point for moving right with reason. 1 point for considers dy dt over dx dt. So they did give a point for writing that. And 1 point for the slope at time 2. Part B. Find the x-coordinate of the particle's position at time 3. Just the x-coordinate. So that's a little fundamental theorem using our initial condition and what we're trying to find with our slope. So x at time 4 minus x at time 2, I always put the larger time first, is equal to the integral from 2 to 4 of x prime, which we have the function for. So x at 4 will equal, I'm showing that I'm putting in my initial condition because I know that that's always worth a point, or usually they're looking for that. And then the rest I can use my calculator for. So clear that out. 1 plus math 9, 2 to 4 of my y1. And I get 1.253. That part was worth 2 points. 1 point for the integral, 1 point for the answer. So that time they didn't give a point specifically for showing that initial condition, but that is part of the problem. That's part of how we get the answer. And remember, we never just put an answer down without showing what we're doing to get it. Part C, find the speed of the particle at time 4. Speed of the particle at time 4. So that's our square root. Since we're finding two different things, I need to say what I'm doing. This is the speed at time 4. Okay. Again, if they weren't asking me for the acceleration, I could just throw down that square root, and that's fine. But since they're asking me for two things, say what each of these is. Otherwise, how would they know that that's what you're finding? So the speed is x at time 4 would be x prime at 4 squared plus y prime at 4 squared. Sometimes I forget and I put the t's here, and if you do that, just put an at time 4, and then in your calculator you're going to do this with the 4's. So that is my speed equation is already stored in for y3. It's already there. So on my home screen, all I have to do is pull up y3 and evaluate it at time 4. And I get 0.575. And now we want the acceleration vector, the acceleration vector at time 4. So the acceleration vector at time 4 will be a vector. It will have two coordinates. The x coordinate will be the second derivative at time 4. The second derivative of x at time 4. The y coordinate will be the second derivative of y at time 4. So remember, we always have to say what we're doing to get our numbers, our values. Now, this will be the derivative of my y1. So evaluated at time 4. So I'm doing math 8 of my y1 evaluated at time 4. So I get negative 0.041. Okay. Same thing this time with y2. So I think I'm just going to scroll up, grab that, go change this to y2. I get 0.989. That was worth 2 points. 1 point for the speed, 1 point for the acceleration. Next up, find the distance traveled by the particle from time 2 to time 4. That's just our formula for distance. Integral 2 to 4 of the speed. That speed pops up so much. Remember, when we're doing the speed, when we're doing the total distance traveled, you will never have values put in for time right here. And again, the square root is stored right here. So all I need to do is the integral from 2 to 4 of my y3. So the integral from 2 to 4 of my y3. .651, and that was worth 2 points. 1 point for the integral, the expression for distance, and 1 point for the answer. Okay? So again, this was a little bit longer than the one from 2016. We had a little bit more to do with it, but it really wasn't too bad. Okay? All right, next up, we are going to take a look at the problem from 2009. I know that this is a long time ago, but I find this problem interesting. So I always like to go, I keep this in the packet even though there have been more recent parametric and motion problems on the AP exam. I still keep this in here because I like it. This was number 3, but it was with a calculator back in 2009. They used to have more calculator problems. So let's read it. A diver leaps off the edge of a diving platform into a pool below. We have a figure at time t seconds after she leaps. The horizontal distance from the edge of the platform is given by x of t, that's horizontal of course, and the vertical distance from the water surface to her shoulders is given by y of t. Okay, from the water surface to her shoulders is y of t, where x and y are measured in meters. Okay, suppose that the diver's shoulders are 11.4 meters above the water when she makes her leap. What are they giving us? That's the distance above the water. That's in the vertical direction, correct? So they are giving us at time 0, the y coordinate is 11.4. That's the vertical distance. dx dt is a constant 0.8. So that must mean that she is moving away. She's moving in the horizontal direction. She's always moving to the right, and that makes sense. She's going to always move to the right until she hits that water. And dy dt is given to us as this. Okay, for time 0 to a, where a is the time that the driver's shoulders hits the water. So that tells us y at time a is going to be 0, because at the end she's at the vertical distance of 0 from the water. All right, part A. Find the maximum vertical distance from the water surface to the diver's shoulders. So we want that y coordinate there. That's the maximum vertical distance. We'll write here at this time the dy dt, the change in y is going from positive to negative, correct? So right here dy dt is going to be 0. So I'm going to say that. So the max vertical distance occurs when dy dt is equal to 0. Okay, so that means 3.6 minus 9.8t is equal to 0. I don't need a calculator for this. That means t is equal to 3.6 divided by 9.8, right? So that's the time right here. Now we need to find y at that time. Y at that time. Well, I have a y coordinate, and I have a new time, and I have y prime, so this is fundamental theorem. So I'm going to say y at my new time minus y at 0 is the integral from 0 to that new time, and now I'm wishing I had stored that in for some letter, but that's okay, of my y prime. So my new y coordinate will be my initial height, my initial y value, plus this integral. And now I am going to use my calculator for that. So I've got 11.8 plus math 9, 0 to 3.6 divided by 9.8 of my y prime. I might go and put that into my calculator. It's not too hard to type in though. I am going to go put that in because I'm having to make sure that that's correct. So I get 12.461, and I will tell you, let's see. Okay, so 12.461. And that is the maximum vertical distance from the water surface to the diver's shoulders. So this part was worth 3 points way back in 2009. 1 point for considers dy dt equals 0. That was the very first thing that we did. 1 point for the integral, our integral here, 1 point for the answer. Okay, part B. Find A. I kind of knew that was coming when they gave me that inequality up here. Find A, the time that the driver's shoulders enter the water. Okay? So, I have these two. I want A, so I'm going to set up fundamental theorem. So, y at time A minus y at time 0 will be the integral from 0 to A of my y prime. I know that y at time A is 0. I know that y at 0 is 11.4. And, A. And I know this y prime. So this was one where, even though we have a calculator, we're going to have to evaluate this by hand. It's not going to be hard, but we need to evaluate this by hand to find A. So I have negative 11.4 is equal to 3.6t, little power rule going on here, minus 9.8 over 2t squared, evaluated from 0 to A. So that's 3.6a minus 9.8 over 2a squared minus, when we put 0 in for t, we just get 0. And from here, I go to my calculator. I'm going to put this in for y1, this in for y2, and find what a is. So I'm clearing all this stuff out. I'm going to put 3.6x minus 9.8 divided by 2x squared in for y1, negative 11.4 in for y2. How long, what's our window? What should our window be? She's not going to be in the air very long, right? And it is a time, so I think 5 seconds is plenty. For the y max and y min, I just need to make sure I include this negative 11.4. So I think I'm going to go from like negative 15 to, I don't know, 5. Okay, so there's my intersection point. I need to go find that. And I get 1.936. There may be a different way to find A, but that's the way I saw to do it. This was worth 2 points. 1 point for the equation. That would be our fundamental theorem equation. 1 point for the answer. Okay, part C. Find the total distance traveled by the diver's shoulders from the time she leaps until she hits the water. So total distance from time 0 to the ending time, which is time A, which we just found. Square root x prime squared plus y prime squared dt. Straight calculator work. So Math 9, oh, I just lost that. I bet I just lost that. Let me go find it again. Okay, I'm going to save that in for A. So X stow in for A, just so I don't lose it again if I move anything. Math 9, 0 to A, square root, X prime squared plus Y prime. And since I didn't type it into my calculator, I have to keep retyping it in. That's X prime squared plus Y prime squared. That's what they gave us in the problem. Okay, dx, actually that's a dt, but I'm using x's, and this is 12.946. This was worth 2 points. 1 point for the integral, 1 point for the answer. And part D. Find the angle theta between 0 and pi over 2 between the path of the diver and the water at the instant the diver's shoulders enter the water. So we're looking for this angle right here. So I'm going to redraw that down here. So she's coming in at some angle. I'm exaggerating that angle, and we want to find that theta value. So I am going to make a right triangle here. Okay, very helpful in finding that angle, right? So I need to know, if I knew this slope, which is something I'm thinking of what I can do in a parametric. I can find that slope. Well, that slope is definitely going to help me find this theta value. So I'm going to find the slope first. So we're looking for the slope when she enters the water at my time A. That will give us that slope right there. So that is dy dt at time A divided by dx dt at time A. Dx dt is a constant the whole time, but dy dt is changing. Dy dt at time, dx dt is always 0.8. Dy dt at time A will be the 3.6 minus 9.8 times my A. That is my dy dt. Let me get to where you can see it. At time A. Okay? And then I'm going to divide that by my 0.8 for my dx dt. So that is a negative 19.219. Now we want our angle. They tell us to make our angle between 0 and pi over 2. So all I need to do is consider the positive of that 19.219 to get this angle. So think about that. This slope is negative 19.219. That means we're going down and then over, down and then over. So this distance is 19.219, and this is over 1. Okay? So when we're finding this angle, we set up a little SOHCAHTOA, tangent theta as opposite over adjacent. Now in my calculator I'm going to be using that whole value, but theta will just be the inverse tan of that. So inverse tan of, well, I'm going to say the negative of that. I wonder if it'll do that. Okay. Yep, it did. So we get 1.519 radians. That part was worth 2 points. 1 point for finding dy dx at time A. If you found that, you got a point, and then 1 point for the answer. So I thought that was an interesting little problem. Definitely would have taken me the whole 15 minutes to do, I think, the first time I did this. Maybe not. Maybe it would have taken more than that, but definitely a longer problem. All right. Now it's your turn. Go refresh yourself. Do these problems.